what we're going to do is we're going to basically add some tools to our toolbox, so to speak. So remember with our first lesson that we just did, and you guys didn't like it, and then I let you just sit in here basically and work yesterday on like trying to understand what you're doing, okay? Now that you have the idea of what you're doing, you were really only using 3 new tools yesterday. You had what the sine, cosine, tangent, cotangent, secant, cosecant, all those relationships, but we kind of knew those from before. And then we learned like those 3 Pythagorean identities, right? And those helped us with a lot of our substitution to manipulate things. Every section we do, you're going to get a bunch more identities or formulas in order to manipulate. So here's the deal with you I'll make, only because Ms. Brady made it with her class, whatever. Okay, so, no, not happy about it. Have a discussion with her for next time. Okay, so for this test and for the final, given the time period that we have, I will include formulas. Okay, that means the 3 main formulas we come across today will be included. It's actually 6, but it looks like 3, but it's 6. Okay. Then the next time, there's like 6 more formulas that we have to learn. Those will be included as well. So when you take your test, I will write those up on the board. So they are called sum and difference formulas, half-angle formulas, double-angle formulas. I will write all those on the board. Pythagorean identities? No. Learn them. They're important. You'll keep using them over and over and over again and should be able to use them without reference. Okay? The double half angles, yeah, when you're studying this, you should be able to use them without reference, but if you went away for a long time and then came back to it, you'd probably have to look them up, okay? So I'll let you have those formulas, okay? So these identities right here are just to point out, maybe you're supposed to prove something and you get here, but the answer says it's supposed to equal this. How do you know those things are equal? So we're going to just talk about a little bit why these are true, but they're just saying, hey, here's how things are related. So I would think about it like this. Let's see. So there are certain relationships you guys started to see on the unit circle, right? Like the cosine of 30 degrees is the same as the sine of 60 degrees. Stuff like that, right? Because it's kind of just like this, like all the same points just in different places, so they have some specific relationships. So these relationships are about location of the angle. So we're just going to talk about why these work a little bit. So right here, they're saying the sine of the opposite of an angle is equal to the opposite of the sine of the angle. Give yourself a little context for a minute. It always helps to simplify it. Plug in a number for the angle, say 30 degrees, okay? I'll start over here. What is the sine of 30 degrees? Think. 1/2. Good. So the opposite sine of 30 degrees is -1/2 for that side, right? Now let's go over here. 30 is still our angle. What is the sine of -30 degrees? -1/2. Not just because someone threw a negative in there, but because -30 degrees is located in a place that would have a negative y coordinate, and so that would make it -1/2. Okay, so do we see kind of why those are equal in the context of the angle? So the reason that works all the time, think about how the unit circle works. If you're trying to find this angle location, you're going to some angle location and you're saying, yeah, here's my angle. Here's the position. The sine of the angle is the y coordinate, right? If you traveled the opposite direction but the same amount of degrees or radians, so if you went this way and you end up at this position, you guys know the number part is going to be the same here, but because it's in the 4th quadrant, it's going to be the opposite, okay? So they're just saying, like we did with our 30 degrees, that relationship is consistent all the time, because whatever degree you're traveling, the only difference between going positive or negative is that you're going to end up on one or the other side of the x-axis. So the only difference there is going to be the sine of the sine, the negative positive part of the sine, okay? So with cosine, it's a little bit different. Because if I pick those angles, like this angle here and this angle here, say this angle's theta and this angle's negative theta, like 30 and negative 30, what's the relationship of the cosines of those angles? They're the same, right? Because on this half of the unit circle, no matter whether you're in first quadrant or fourth quadrant, they have the same cosine. If you went more than 90 degrees and your angle ended up over here, well, go more than negative 90 degrees, you end up over here. Again, they're going to have the same cosine. They would just both have negative cosines now. Okay? So with cosine, the angle and the negative angle have the exact same value. With sine, they have opposite values because sine is referring to above and below the x-axis. Okay? Tangent follows the same rules as sines because of the relationship as tangent, and this does have some kind of throwback to, remember when we did inverse functions and the sine and the tangent kind of operated, we picked angles from the same area for those, okay? Because they had the same quadrants that overlapped or whatever with positives and negatives. So sine and tangent kind of work the same way. Okay? So this, I'm just throwing this out there because if you see in your book that you're supposed to prove that it's equal to this and you're getting this, you just have to do one last piece of substitution. It's okay because this is an identity, so it says this is like a thing that we can use to substitute. This is always true, and we can do that if we have to for one last step. Okay? Is this all right with everybody? All right, so just another list of identities. All right, now we're going to prove something. This is the part that's a little bit hard. Okay? So basically, we're going to get to some formulas today. The formulas we have to learn how to use. We'll learn how to use them. We're going to use them two ways. One, in the same context you were using the formulas and identities that you learned yesterday. So one purpose of them is going to be to substitute them into equations to change the way one side of the equation looks to prove it's equal to what's on the other side. Okay? Just new options. All right? Another way is to give us another way to calculate things. For example, after this unit today, in your homework, you will be asked the question, what is the sine of 75 degrees? Exact value, no calculator. Okay? Do you guys know the sine of 75 degrees? No, that's ridiculous, right? That's not special triangle action. Okay? However, 75 degrees can be written as a sum or a difference of two angles that are involved in special triangles. Give me a different way that I could think of 75 that involves angles that are special angles. 45 and 30. Sure, so 75 can be written as 30 plus 45. But we don't know enough about how sine and cosine work. I can't say like, oh, the sine of 75 must just be the sine of 30 plus the sine of 45. Yeah, not that simple. Okay, you can't just add together the things you want. But there is something I can do with 30 and 45. I just got to figure it out. So what we're going to do is look at how someone figured out one of these formulas, but we're not going to look at all of them. It's a long process, not going to lie. So we're going to look at how they did one, and then we're just going to learn the formulas. But then at least we understand where the formulas came from a little bit. Okay? So I'm going to try and color code my diagram here. So this large angle right here, this is angle alpha. Okay? Don't be scared of the names. Greek letters, okay? Alpha, right? So alpha is this angle, meaning this point right here on the unit circle is the position that I would end up at. And remember, our x-coordinate has to do with the cosine of the angle, and the y-coordinate has to do with the sine. So I would venture to say that here the x-coordinate could be called cosine of alpha, because the angle size is alpha, and the y-coordinate could be called sine of alpha, right? Like I asked you guys, what's the sine of 30? And you said 1/2 because 1/2 is the y-coordinate at 30 degrees, right? All right, now, this smaller angle right here, another angle, new name, will be beta, okay? There used to be a grocery store called Alpha Beta, in case you guys didn't know that. Random fact. Okay. So this is beta, which means when I get to this position on the unit circle, the coordinates here would be cosine for the x-coordinate, but this time of angle beta, because that's where I'm at, and sine for the y-coordinate, but again, this time of angle beta. Everybody okay with just like, these are the things on the diagram, this is what's going on. Now, I'm going to measure a segment from here to here and calculate how far apart those points are. My purpose in doing that is that this distance that I'm trying to calculate, I don't want it to be about angle alpha or about angle beta. I want it to be about alpha and beta being added or subtracted, like how we said 75 is 30 plus 45. Then I got to know what to do with the 30 plus 45 part. So if you guys remember from geometry, if you guys had an angle that I said, okay, this angle is 70 degrees, and then I drew this in and said, oh, this part's 40, what's the other part up here? 30, because 70 minus 40 would be 30. Okay? So my big angle right here is called alpha, and this small part of it is called, so this other part of it could be called, all right? Is that okay with all the naming that's going on here? All right, so we just understand how everything's being named. So again, who came up with why they're measuring? I'm showing you the proof of their theorem, so they probably came up with a conjecture and then they went through and proved it. But I'm choosing this distance because it's related to this angle measurement, and this angle measurement is not a straight up angle I know stuff about. Instead, it's a sum or a difference between two, like how 75 is going to have to be something to do with 30 plus 45, okay? So now, if I want to calculate that distance, does anybody remember distance between points? How do we calculate distance between points? Justin? Yes. Okay, so we have this giant square root. And underneath the square root, we subtract both the x coordinates and square it, plus we subtract both the y coordinates and square it. People remember the setup of the distance formula? So if I'm trying to find the distance between these two, the bummer is my x and y coordinates have trig functions in them, so calm down. Okay, instead of saying x and y, I have cosine alpha and cosine beta as my x coordinates, sine alpha and sine beta as my y coordinates. So I'm going to do cosine alpha minus cosine beta and sine alpha minus sine beta. Okay? We all right? I don't want the square root there. So I'm going to go ahead and square both sides of my equation to not have to deal with the square root. So that will make this d squared, but then when I square this entire side, that will basically get rid of that radical for me. Okay? So now I have d squared, and I'm going to write what it's equal to, and I am going to expand out these polynomials. Now, what I found from second is that we kind of forgot just how to deal with basic stuff. All right. X plus 5 squared. When you square x plus 5, what do you get? Oh, thank goodness there were 3 terms. Okay. So we get x squared plus 10x plus 25. We can see that that's that squared, that's that squared. This is coming from when you distribute, or if you guys like to call it FOIL, whatever, you end up with 2 terms in the middle that combined. It's basically 5x, but it's 2 of them. So it's 5x times 2, which is giving me the 10x. So now going back to this stuff, if I have cosine alpha minus cosine beta squared, I'm going to get cosine squared of alpha. That's that first term, right? What's my middle term going to be? When it was x and 5 times x made 5x, and I doubled it. When it's minus 2, cosine alpha, cosine beta. Yeah. Because you can't, it's kind of like the log, right? If you had the log of 6 times the log of 10, you don't just say, well, that's the log of 6 times 10. No, because the log does something to that number before you multiply it together, so you've got to keep that cosine or sine in front of that. And then my last term for that one would be cosine squared beta. Then I got to do all the same thing for the parentheses where the sines are being squared. Okay? Now that we get the pattern, hopefully get this. So this is going to be sine squared alpha. I'm probably going to run out of room. Maybe not. Let's see if I can write really slow. 2 sine alpha, sine beta. Who cares if you guys can read it? I just got to fit it. No, I'm just kidding. Plus sine squared beta. Whew. All right. You kind of can't read it, but all right. So I did this to simplify. What do you guys think? I'm so smart, right? Okay. There's actually some really pretty things that are going on the, yes, I said pretty to describe mathematics, okay? There are some really nice things going on the right-hand side of this equation. It's just about whether or not we can see them. So there are some things over there that we should be able to simplify. Do we see them? Taryn.
Cosine squared alpha equals sine squared alpha.
Good. So we learned yesterday in a Pythagorean identity, if you have cosine squared of an angle plus sine squared of the same angle, what does that really equal? 1. So this plus this is really equal to 1. Okay, so I'm going to go ahead and just go like this and write 1. Is that okay with everybody? I didn't cancel them out. You guys, okay? Oh, there's another one, right? Cosine squared beta plus sine squared beta also equals 1. So 1 plus 1 is 2. I can do that. Very good. Yes, I'm good. Aren't you glad I'm your math teacher? I've got my 1 plus 1 down. Okay. Sine alpha, sine beta. Okay, I can't really do anything else. That's it. It's as simple as it gets. So that's not that encouraging because it's like, well, that's not like that useful. Okay. And it also still has D in it, which doesn't really help me. I really wanted to relate it back to something about this alpha minus beta. Okay? So here's what I'm going to do. I'm going to actually go through this process again so that I can compare two distances that I know are the same and try and set what they're equal to each other. Kind of like when you guys solve a system. Like if you have y equals 3x plus 2 and y equals 5x minus 1, you can set the 3x plus 2 equal to the 5x minus 1 because they were both equal to y. Right? That allows you to solve the system. So what I want is another equation that has cosines and alphas and betas in it that's also equal to d squared. So I can just set it equal to this one, not worry about d anymore, and just try to find a relationship with these cosines of alphas and betas. Okay? But in the second formula, they really want a sum or a difference in it, because that's what we're really trying to come up with, our new formulas for the sums and the differences. So what I'm going to do is I'm going to redraw the alpha minus beta angle. I'm just going to draw it in a new spot. I'm not going to change its size. I'm just going to position it in the standard position. Does anybody remember what standard position means when we first started figuring out there was a circle on a coordinate plane and we could put angle positions on it? Michaela? Good, that we have the initial side here, okay? So what I'm going to do is I'm going to draw this angle. It's still going to be angle alpha minus beta. Is that okay with everybody? This is going to be the same size as that, okay? And what that means is if I connect these 2 points, it's the same distance as they were right here because they're part of the connection of the same arcing angle. Is that okay with everybody? So my angle's the same size, which means the D's are the same, okay? Same distance, same angle size. Connect 2 points of the same distance. But I've put the distance in a new place. So if I work out the distance formula for this D down here, it's going to look different, but it should be worth the same at the end. What are the coordinates of this point right here on the x-axis on our unit circle? Not 0, 0, 1, 0. And what are the coordinates of this point right here if this is angle alpha minus beta? Okay, good. Cosine is the x-coordinate, sine is the y-coordinate, and the angle just got super ugly on us, right? What's the angle? Alpha minus beta is just the angle. So x-coordinate's cosine, y-coordinate's sine. That we already knew, right? But instead of the angle just being alpha, which was this big one, or just being beta, which was this small one, this one had a more complicated name because we got it from doing arithmetic of the other two. So the angle name here is alpha minus beta. Sorry, I can't fit it all in there. Let me write it right. And then the sign of alpha minus beta. Okay? So if I'm going to now do the distance formula between these two, I should get the same thing that I got previously because it's supposed to be the same angle with the same little distance segment connected to it. So this time, if I wrote my distance formula, myself space because we know I'm going to run out of room. Okay, x-coordinates. Cosine alpha minus beta is one x-coordinate. 1 is the other x-coordinate. I'm very thankful for the 1 at this point, right? It's nice to have a number. So this is cosine alpha minus beta, and then minus 1 squared, plus sine of alpha minus beta minus 0 squared, because 0 is the y-coordinate. Does everybody get? I'm just repeating the same thing I just did. But instead of measuring D from the points that had cosine alpha, sine alpha, and cosine beta, sine beta, I just moved the angle to a new spot. The distance should still be the same, but now the points are cosine alpha minus beta, sine alpha minus beta, and 1, 0. So I'm using those 2 points in my distance formula. Okay? All right, so I'm going to square both sides, get rid of the radical. Okay. And then I'm going to expand it out just like I did before. So cosine alpha minus beta minus 1. So remember, first term gets squared. Cosine squared alpha minus beta. What's going to be the next term in this polynomial? Max? Good job. Okay. Minus 2 cosine alpha minus beta. Because remember, it would be cosine alpha minus beta times negative 1. There would be another one of those. Get over the alpha minus beta. Who cares how ugly the angle is, right? It's all right. Okay, and then the last thing we'd do is 1 times 1, which would be 1. The next one's really hard. Okay. What do you get when you square this binomial? Sine squared alpha minus beta. What else? That's it. 0, right? Love 0. What did they do in the number system when 0 wasn't there? I don't know. Okay. So we got this. Okay? Can it get any better? Can we make it look better? Or are we just stuck with all that? 1 for what? Sine squared. Oh, yeah. It doesn't matter how ugly that angle is. Cosine squared plus sine squared, same thing after them is 1. So that's going to become a 1. We already have another 1 right here, so together those will add up to be 2. This looks a little better. Okay, so again, try to remember their purpose in doing this. We're only going to do this once. Now you can see why. So the purpose was to build a formula for sums or differences. So I really want to build a formula for this right here, the cosine of an angle minus another angle, because I'm not sure how that works, and I'm trying to figure out. I know I can't just subtract the numbers. Okay, Taryn? Okay, good. So the first thing we can do is set the two equations we now have together, because both of them are equal to d squared, and we have said over and over again that even though these d's were in different places, they are the same distance because they were both attached to the alpha minus beta angle. Okay? So I'm going to set the two equations equal to each other. All right, so Taryn said the 2's can cancel, so subtracting 2 from each side gets rid of these. Max? 1 become 2. Oh, because there was a 1, and then there was a sine squared plus a cosine squared that would also be a 1. It would become 2. Thank you for asking when you weren't sure. All right, so we subtract 2 from both sides, and those 2's are gone, completely zeroed out. Done. Okay. All right, what else can we do to both sides that might make this look simpler? Molly? Yeah, I'm going to divide by negative 2. And when I do that, I get cosine alpha cosine beta plus sine alpha sine beta equals cosine alpha minus beta. Whew, this is what they were aiming for. So this is the proof that this formula is allowed to exist. Okay? So this formula exists and is allowed to exist because we proved that it works in a general sense, not for a specific number, but for anything, okay? Alpha, beta, okay? Now, there's 1 when the angles are added together. There's 1 when the angles are added and subtracted for sine. There's 1 when the angles are added and subtracted for tangent. So there's 6 formulas total. We're going to write them kind of 3 formulas because there are some patterns we can see. We just have to remember where to put the signs properly. Kind of like when we learned the cubes, okay? The cubed patterns, how to factor a cubed minus b cubed. It didn't really matter if they changed it to a cubed plus b cubed. The numbers all came out the same. We just had to put the signs in the right place. That's kind of what we're going to look at here. All right, so to summarize. I can go back to the screen later if you guys need to pop some. All right, so here's what you'll want to write down your formula. So that was where do I come from? Why am I allowed to exist? Now you saw it. Do you want to do it 5 more times? No. All right. So we're going to look at one proof and understand someone didn't just make these up. They went through this idea. They saw a pattern. They proved that it works all the time. And so then they came up with their formula. So for cosine, we just saw that cosine of the alpha angle minus the beta angle, and yes, I know I wrote my minus kind of low. I kind of did it on purpose, okay? Because I'm going to just come put something else over there in a minute. Okay, and this, yeah, okay. Not a big secret, kind of. All right, so we got this. So for me personally, now I know you're going to have a little formula list, but if I was trying to at least remember this, notice that the signs are opposite, but these are so nice. It's like all the cosines are together, all the sines are together. So that kind of helps me in general. So when you have to learn this like next year. Guess what? If it's a sum of an angle instead of a difference of an angle, the only thing that changes is, okay, don't just write these in whatever version you want. I wrote them in this order for a reason. Now in your book, they separate them. You can write two separate ones if you want. If it's cosine of an angle plus another angle, then it splits up as cosine of the angle times cosine of the other angle minus sine of the angle times sine of the other angle. If in here it was subtraction between the two angles, then over here it's going to be addition. So do you understand how to read this? Because in some books it's printed like this. In yours it's not. They nicely split them up into difference formulas and sum formulas, but they have the same patterns except for the signage. Okay? Now, for the sine function, we also have a sum or a difference formula. So the sine is nice with the sines. In other words, if it's plus in here, guess what? It's also plus here. And if it's minus in here, it's also minus here. But it's not as nice about how these are packaged, okay? It's sine of the first angle, cosine of the second angle. And then over here, it's cosine of the first angle and sine of the second angle. I know. So I just always remember one of them's nice here. If it's nice here, it's not nice here. Okay, one of them's nicely organized here, but then over here I have to remember to switch it. I don't know. But you guys don't really have to memorize them yet, so you're fine. Then for the tangent. What's the problem? Who's happy that Miss Brady made a deal with her class now? That you get the formulas. That they get the formulas. So then I told you guys I would give them to you too. Yeah. Marlon's like, good. Whew. That's it. That's it. There's no other ends. That's it. Oh, sorry. I keep standing in front. There's no catch. Calm yourselves down. Sometimes people just decide to be nice to you. Just figure if I'm being nice, that means it must be really hard. Just kidding. I'm just kidding. Okay. Are we good? No. All right. So again, what are we going to use this for? One, now if I'm trying to verify an identity and something shows up like this in the identity, or something shows up like this in the identity, I could take this and turn it into this if that's helpful, or I could take this and turn it into this if that's helpful. Okay? The Pythagorean ones you guys have to know and memorize. So know those ones, memorize them. They're very commonly used, okay? These ones a little bit less. The other thing we would use them for, we can now calculate the sine of 75 if we wanted, okay? It's not the sine of 30 plus the sine of 45, okay? We would use 30 and 45, but in this formula here, all right? So, a couple of examples of that. All right. Your book has a section, it calls these cofunction identities. But here's my thing. You don't have to have them memorized. Here's why. If I see this in a problem and I'm somehow supposed to do something to turn it into this, well, guess what? This is sine of an angle minus another angle. Flashback. sine of an angle plus or minus another angle can be expanded out this way, right? So I don't memorize this. You can if you want. Okay? Instead, when I see this, I apply the property that we just talked about. So remember, if it's sine of a sum or a difference, it uses the same sum or difference. And then the formula said. Did you get that? The formula said sine of the first angle, cosine of the second angle, minus cosine of the first angle, sine of the second angle. All I did was use pi over 2 and theta is as my alpha and beta angles in the formula we just looked at. Is that okay? So look back at your formula. All I did was use this as like my alpha and my beta in the formula. Okay? Now I actually know some of these. You might think you don't know, but you actually do. And if you don't know, you better find your little plate. Okay? Yeah, so sine of 90 or pi over 2 is 1. And cosine of 90 or pi over 2 is 0. 0 times anything is 0. 1 times anything is that thing. Okay? So, is sine of pi over 2 minus an angle equal to cosine of that same angle? Yes. Okay? Do I have to have it memorized? No. I could use the formula and figure it out if I need to. Is that all right with everybody? So, your book has these written as identities. You can memorize them. You can use the formula to figure them out later. Todd? Yes. Okay. Do you guys get what he's talking about? So, good job, Todd. All right. Remember our sine function graph went like this? Okay. The sine of pi over 2 minus theta, I might have to write this a little bit differently, but I'm going to write it the way that we saw it just so people could see like this or like... So this is like a horizontal reflection and a shift to the right pi over 2. Okay? So if we horizontally reflected it, it would go like this. Then if we shifted it to right pi over 2, which is 1 mark on our graph, it would look like this. Notice then if on the same graph I went to graph the cosine function, right? It's a continuation of that. They are the same function, okay? There's also reasons from the unit circle why mathematically you can subtract an angle from 90 degrees and end up, like think about the 30-60 relationship, right? Think about like a 30-degree angle. Okay, what's the cosine of 30 degrees? Come on, people. We're at 3 over 2, okay? If I had 90 minus 30 degrees, what does that give me? 60. What's the sine at 60 degrees? We're at 3 over 2 because 30 and 60 have that special relationship. It has to do because of that other 90-degree angle in the triangle that makes that relationship. So you're going to see some of those patterns as well. So all of this stuff relates back to numerically. You can see how it works on the unit circle. Graphically, you can see how it works with the stuff that we've graphed before. So again, these identities can make sense to you from those perspectives, but do I have to have them memorized? I can use, if I know this one identity, I could figure it out that other way, okay? So know that they're there, but don't feel like you have to memorize those ones. All right, so we're not going to do part B. We know the cosine of negative 120 without using sum or difference. That doesn't mean that in your homework you might have some problems that actually ask you to use sum or difference for something I know you could do without it, but just to get practice using that specific kind of formula. But let's do the sine of 105. Okay, so is 105 a special angle where you'd say, oh, I know the sine of 105 immediately? No. Okay? Oh, gosh, I'm going to die one day just by falling. I'm like the clumsiest person alive. It's really sad. Okay, so I struggle daily in my daily life. Okay, so the sign of what? How do I want to rewrite 105 to figure this out? Brian? Sure. Notice that he strategically picked angles he did know something about. Now, no distributive property here. Sine is not a number. It doesn't just get to go in and multiply everybody, okay? It's a function. You've got to use the formula that we just talked about. So it says this would be sine of 60, cosine of 45. Again, I'm using these as my alpha and my beta, okay, in the formula that we just talked about. Then it would be plus cosine of 60, sine of 45. And then I'm supposed to know these things. That's why I picked 60 and 45, right? Sine of 60 is root 3 over 2. Cosine of 45 is root 2 over 2. Cosine of 60 is 1/2. And sine of 45, root 2 over 2. So I get rad 6 over 4 plus rad 2 over 4. And really the best I can do, exact value, okay? Just to say it is rad 6 plus rad 2 over 4. Okay? So, way number one that we're using this new formula that we figured out. So we saw a lot of relationships and proof at the beginning, okay? But now we're saying, okay, how do we use it? Well, we use it to calculate things that before we thought we couldn't calculate without a calculator, okay? By splitting it up into two angles, our alpha and our beta, okay, or whatever you want to call them, A and B, two angles that we do know the functions about, applying the formula and then doing the calculation. Okay? Is this all right with using it for this purpose? All right. Next thing we want to do, first there needs to be a correction made, I believe. Sucks to verify something that doesn't actually work. So this needs to have a negative in front of it. Okay, so we're going to look at part C. It needs to have a negative right there, I believe. Okay, so put that in your note guide. So let's say you were asked to verify an identity. This is what you were asked to do on last night's homework, right? And the day before, and something that when we first saw it, we were like, how do you even come up with ideas? But hopefully in trying more and more problems, you're starting to see little things that might trigger you to do this instead of this because you saw that on the other side, so it makes you want to do this. Things that the experience gives you that nothing else can. Well, when you see this, what are you going to do with that? Taryn? You cannot multiply both sides of the equation by something because you are verifying that something is true. What's that? -1 over -1. We can do that. But so see how you're already thinking in your head the expanded out version? So we should just do that first. Expand it out. Okay? So these are things like proofs. Mathematicians can't just skip 5 steps in a proof and write something down. You have to write it down so people can read it and know there's justification with each step that you're doing. So first thing I would do is write out the expanded idea of this. Again, that's using the formula where theta is like our alpha, right? And pi over 2 is like our beta. What else would I do with this, right? This is like a big hint. This should actually be easier when you get one of these on the test than like the ones that you had last night for homework. Because it's like, you look at this, immediately you should think sum and difference formula. It's kind of the only applicable thing to something that looks like this, okay? So we have sine theta cosine pi over 2 minus cosine theta sine pi over 2. And then we'll do, just like we did before, we're going to calculate the ones we know that we can calculate. So cosine of pi over 2 is 0, so that part's going to be gone. Okay, that's because this was 0. I didn't just cross something out, okay? Annika? Yes. Sine of pi over 2 is 1. So we get negative cosine times 1, which is just negative cosine. They want it to look like this? Fine. I know that the cosine and the secant are reciprocals, so I can just rewrite it like this. Yeah, Taryn. Oh, I gotcha. Just use the opposite of that one. Right. So he's saying the cofunction ones. So I didn't do that because I'll be perfectly honest with you guys, I don't have them memorized. I actually do have the sum and difference formulas memorized because I had to do it in high school and in college. But if you memorize it, that's fine. And then if I ask you, just say, I just used the cofunction identity. That's totally fine. But I'm not going to give you that formula. I'm going to give you sum and difference formulas, and then what we're going to learn later, double and half angle formulas. Okay? All right. So the other way we're using it is doing the same thing that we were doing before, but new tool, right? Now when we see two angles being added or subtracted inside a sine, cosine, or tangent, we can expand it out and then keep working with it. Right, the last type of problem, question or no? The last type of problem that you're going to see on your homework is really to prepare us for what's coming up. So basically there's these. There's the double and half angle formulas, which again, you'll learn the formulas, you'll get to use the formulas on the test, and they'll be, again, just another tool to manipulate things and be able to make them look like something else, okay? And then in the end, why do you learn all these tools? Not just to verify and prove things are true, but to solve equations. So the last thing we're going to do is solve equations. But here I have a solving equation problem right here. I just want you guys to think about it logically. So first what I want you to do is change this because this is a little crazy. So we can either expand it out, right, using our sum and difference formula, or we can try using our cofunction identity or whatever. Okay, I don't know it, so I'm going to write it out. So sine of theta, cosine of pi over 2. Again, this is like my alpha, and this is like my beta, and I'm just using that same thing. Oh, no, this is nice. Minus. Okay. And then I'm going to do my cosine of theta and my sine of pi over 2. And then I'm going to simplify this left side just like I did before. The giant dot, I started to write plus, and then I realized I was wrong, so I scratched it out. Okay. So cosine of pi over 2 is 0, so this term is not going to help us any, right? Sine of pi over 2 is 1. Now you guys might think, oh, this isn't going to equal. Well, you're right, okay? Because are we trying to verify that this is true? No. We're trying to give them specific angle measurements between 0 and 2 pi that this will work for. Okay, but it's not going to work for everything. I'm trying to pick out. And maybe there's no solution sometimes, just like with lines and systems and things like that. So once we've learned all the formulas, we're going to learn kind of a different way of solving. But so now really my goal is to find an angle between 0 and 2 pi. So just picture it. One time around the unit circle where the opposite of the cosine of the angle is equal to the sine of the angle. Now, I'm just going to pick one way off base just to tell you guys if it makes sense. Let's say I pick 30 degrees. Tends to be my number of choice today, right? Okay. So I pick 30 degrees. I know that the coordinates at 30 degrees are root 3 over 2 and 1/2. Correct? Does 30 degrees, or pi over 6, is it an answer or a solution to this equation? In other words, does the negative cosine of 30 degrees equal the sine of 30 degrees? Well, the cosine is root 3 over 2, so the negative cosine would be negative. Is that equal to 1/2? No. What kind of angle would these quantities be equal to each other at? 45s, because I need the same number on each side, right? So am I going to pick the 45 right here? No, because what's the matter with that? I mean, I'm in the right realm because at least the numbers match, but do they make this true? Root 2 over 2 and negative root 2 over 2. What does need to happen? One needs to be a negative and one needs to be positive. So second or fourth quadrant. So what is the 45-degree angle over here in second quadrant in radians? In radians. 3 pi over 4. And then in the fourth quadrant, 7 pi over 4. These are two numbers. I used radians because they gave me the restrictions in radians. So these are two measurements between 0 and 2 pi that make this true, and the only two measurements that make this true. So I would say my answer is that the angle could be 3 pi over 4 or 7 pi over 4. Is this all right with everybody?